Imagine you have a Pinewood Derby tomorrow, and you need to make your car go the fastest to get that big gold medal to make your dad finally be proud of you. How are we going to do that? In this experiment, we're going to see how a change in the mass of wheels, a change in the radius of the wheels, and a change in the location of the center of mass will affect the final time that it takes for the Pinewood Derby car to get from the top of the ramp to the bottom of the ramp.
So, the three cars we'll be looking at is car A, which has a center of mass towards the back of the car, low mass wheels, and a small wheel radius. Car B, which has a center of mass towards the front of the car, high mass wheels, and a small wheel radius. And then finally, car C, who has a center of mass towards the back of the car, low mass wheels, and a large wheel radius. And please keep in mind that the total mass of all the cars is the same.
When we're evaluating how changing these variables will affect time down the slope, the first question we need to ask is how do we calculate time? Using the kinematics identities, we know that time is equal to distance over velocity. But in this case, we have a period where the car will be accelerating down the slope due to gravity, and a period where the car will no longer be accelerating, assuming friction and air resistance are negligible. In this case, the velocity we need to use for the first section, d1, is the average velocity during the acceleration period, or the final velocity over 2. And in the second period, d2, we just need to use the final velocity of the car had when it hit the horizontal plane. So we know that we need to solve for the final velocity. We can use an energy lens to show that the change in potential energy of the car will convert into kinetic energy of the car down the slope and rotational energy. We can substitute in our variables, noting that rotational energy, omega, will also become velocity final over r. Simplifying this equation, we will see that velocity final is equal to the square root of mass of the body times the force of gravity times the height, divided by 1/2 mass of the body plus 1/4 mass of the wheels. We can see that in this relationship, increasing h, or the height from the horizontal plane to the center of the mass on the slope, which can be done by moving the center of mass back on the car, will increase the final velocity, decreasing the time spent. Increasing the mass of the wheels will decrease the final velocity or increase the amount of time. And notice that in this equation, changing the radius will have no effect since this variable is canceled out.
So moving back to the cars, we can see that car A and car C have centers of mass towards the back of the car and low mass wheels, in comparison to car B, which has a center of mass towards the front and high mass wheels. Therefore, with the increased final velocity of car A and car C, they should tie for first, with car B coming in second.
As seen through the previously explained equations, we're able to calculate the final velocities of car A, car B, and car C. Car A and car C will have a final velocity of 4 meters per second, while car B will have a final velocity of 3.28 meters per second. This will result in car A and car C crossing the finish line at the same time of 1.05 seconds, and car B passing the finish line at 1.3 seconds.
Using Tracker, we were able to calculate the starting frame from the car at the top of the ramp compared to the end frame when the car crosses the finish line. So car A started at 478, ended at 549, leading to a time of 1.183 seconds. Car B, starting frame 216 and frame 301, ending in a time of 1.41 seconds. And car C started at 391, ended at 467, ending with a time of 1.26 seconds, which proves that car B was the slowest.
So we believe that our estimates might be off for the following reasons. Variables such as friction and air resistance were unaccounted for in our equations. We made the assumption that the wheel mass of the foam board itself and the skewers is 0. And there were external factors such as imperfections in the board and stuff like that that we didn't account for.
Now we ask the question, where do the cars need to be to finish at the same time? To this, we set the times to be equal. We know that time is going to be distance over velocity. In this case, we're going to have to split it up due to a difference in acceleration during different times. We split it to components here and here. We can now use our trig functions, and we're assuming theta is equal to 30 in this case, to solve for d1, the distance. And then knowing that the velocity is equal to previously derive the equation, we can substitute that in and solve for the height.
In theory, these equations would allow us to calculate at what different heights the cars would need to be at to finish at the same time. Unfortunately, we are unable to prove this aspect experimentally due to some testing constraints. Moving a car further up the ramp will increase the final velocity, but it will also increase the total distance needed to be traveled by a car. Over a longer distance, this will be made up for by the final velocity, and the car placed higher up will catch up. But due to limitations in the size of the ramp and the size of the flat available to us, as well as the specific physical properties of our car, we are unable to solve this equation with the given constraints and with our current knowledge of equations.